If you're ready, we can start. I will not speak very loud, and I see that your sound system, I don't know if it works or not. However, can you hear me well to the end?
No.
Not very well. Better? Okay. Let's try. Let's try. Okay, so this presentation, I will try to keep it short in order to leave you more time to work. And it will be our work, it will be in 3 times: my presentation, the development of the work, and the presentation of the works at the end. So, some key requirements. Something that okay, I am coming from 3 days ago, a lecture given at the Space Renaissance Brewing Festival, and my presentation, my lecture was about utopias, a new feasible utopia for this century. And so I just brought 3-4 slides from that presentation here. I will not develop the discourse on utopias, but just to give a reference and to enlarge our vision. So, some key requirements to design a very utopia that is a beautiful place, not an unexisting place, because the word utopia means an unexisting place. But a utopia means a beautiful place that could exist if we are smart enough to do it. So, growth is the main requirement, since any climate-stable civilization will quickly decay and collapse. 100% sustainability is the logical second requirement for any presentist vision of development. 100% inclusivity, that doesn't mean any kind of automated welfare for everybody, yet to assure the platform or the resources necessary to allow each individuals and communities to get well if so they wish, thanks to their own ingenuity, fantasy, decisions, capabilities, and initiative. Tailored for the present, not for the future. We don't need to have a perfect society in 1 century. We need to have a better development now. And all what it will be in 1 century depends from our decision now and what we start to do now or we don't. So our descendants' life in 200, 2100 depends upon our decision. We have to start working now. So, thinking about utopias, I think there is no better utopia than the United Nations 17 Development Goals, the so-called Sustainable Development Goals. So, who are the utopias? Is us is the space community, the space humanists. Are we the utopias? No, it's UN. So let's have a look at their Sustainable Development Goals. So they present all of the goals all together on the same level as if they were perfectly equivalent. And it is useless to think to start first with one, first with the other one. So we have, let me say, humanity in life condition goals, like no poverty, zero hunger, good health and well-being, quality education, gender equality, clean water and sanitation, affordable and clean energy, reduced inequalities, sustainable citizen communities, responsible consumption and production. And then we have environmental goals like climate action, life below water, life on land. And we have, let me say, social conditions or methodology indication, that is peace, justice, and strong institutions and partnership for the goals. Now, if we look at these goals all together, we can never got these goals. We have to reorganize the goals in their correct hierarchy. So we have 3 goals that are fundamental. They are key pillars for the realization of the other goals. And these are the affordable and clean energy, decent work and economic growth, industry innovation, and infrastructure. If we don't have these 3 goals realized, none of the other goals will be feasible. So we can reorder, re-put in a better architecture the UN goals, keeping the three basic goals, the pillars on the bottom, because they can sustain all of the other goals. So the human life goals and the planet Earth environment goals and the methodology goals. By the way, the methodology goals are also, these goals are an outcome of the basic pillars, because if we don't have industrial development, if we don't have social growth, we will not have peace, and we will not have partnerships, and we will have only an increase of conflicts and wars and social conflicts and so on. So, but the point is, so let me try to move this thing because it's making noise. Okay. The point is, okay, are these three pillars sustainable by themselves, considering that we are 8 billion people on Earth, that we have enormous problems of energy, climate, pollution, and, by the way, we grow very much in a closed system. And now we are feeding the bars of the cage, because the Earth, materials are not enough anymore for development of 8 billion people. So the point is that we cannot get to clean our environment if we don't have these three pillars. But we cannot keep on developing these three pillars, because we will worsen the climate and environmental conditions. So what is the point? The point is that we need to have an 18 goal that in civilian space development. Only opening the system and starting to develop outside our boundary of planet Earth, we can really restart an industrial development and economic growth and innovation, global economy, and energy, clean and abundant energy, taken in space and used to develop the space infrastructure. So this is the situation. The really sustainable development goals need an 18 goal. Without that, it will remain an utopia. It will never become an utopia. So this is the problem. So why am I saying this? Because in 2021, the association that I founded 40 years ago, Space Renaissance International, had its third Congress, and we made a final resolution. That indicates some goals to be obtained before 2030 and to work to promote them before 2025. So the most relevant fact is the development and consolidation of reusable rockets, see our previous goals, now leading to fully reusable space vehicles like Starship. Such an epochal development will reduce the cost of a seat to orbit under 1 million, opening the way to industrial space settlement and civilian space development. As stated by the Space Renaissance Manifesto, the expansion of civilization into outer space is the only way to overcome the current global multiple crisis in the so far philosophically closed world, and to restart a vigorous growth in the realm of the solar system. Such a glorious future is not automatic, not guaranteed. Evolution was by trial and error, and we don't know yet whether our species will be a success or a failure on the history of life in the universe. The state is to evolve into a solar system civilization or to be thrown back to a stone age should we remain closed within the boundaries of our mother planet. So these are some of the goals that we detected and our Congress approved in the final resolution in 2021. First one, not going back, but going forward to the forward. Develop proper industrial infrastructure to produce fuel in space from lunar and asteroidal materials, also mining resources such as water, rare earths, precious metals, and helium-3. Space debris recovery and reuse, because space debris are a big problem, because it's a kind of cage around Earth that will represent a danger for any travel to space, but they are also an opportunity because it will be possible to recover them and to reuse them in order to produce materials for developing the space infrastructure. Then enhance life protection in space. If we are going not only to explore space, but to live and to work there, we need to face two main problems. First one is the cosmic radiations, that is a danger for human life. And the second one is to develop artificial gravity in order to avoid the problems to our physiology caused by low gravity. You know that we are experimenting with zero and low gravity since 60 years, but we never started to experiment with artificial gravity. And that is a very needed thing to do. Okay, so start experimenting with simulated gravity, supporting the development of 100% reusable space vehicles, not only low cost, but also safe and reliable, and ergonomics for civilian passengers, not only for astronauts, because we need civilians to start traveling and working in space. Then produce food in space, and to think about the green environment on space habitats. This is very important, not only for our biology, but also for our psychology, because we are used to green environments on Earth, and we should continue with this use also in space. So, having said that, let's come to our workshop. Each team, so at the end of this presentation, we will try to form a certain number of groups, smaller groups, maybe 3 or 4 persons each. We develop a basic statement of work for a project. Phase A, feasibility, call for tenders. So I don't know if some of you already have some experience with the typical European Space Agency system of call for tenders. However, they work normally by statement of works and asking companies to make their offers to develop some project. Okay, so we will simulate. We will simulate to be so we can also dance at the end. The end, we will simulate to be European Space Agency personnel, drawing call for tenders, companies, and that will mean that for a number of projects, we will develop the basic requirements, so the basic work breakdown structure, the basic work package description, these kind of things. Okay. So each statement of work should include science, technology, and engineering hypotheses, social and psychological issues, life and health protection, priority to human and humanist requirements. It means that we have to think about the builders, the technicians, the operators, the users, the final products, and the final users. Route estimation of costs, considering fully reusable space vehicles available. So let's think if the Starship is only operative and working. A basic work breakdown structure, a basic work package description, including deliverables, a basic time scheduling with milestones, conceptual elements for business plan. This is the last one that we talk about. Fantastic.
Okay. Better? Yeah. Okay, great. So each team will present their elaborated SOW during the third session of the workshop. Optional, if you will have time, you will also think about which mix of expertise will be required by proponents, which quality standards will be required to be applied. I mean, I don't know, ISO 9000 or ISA standard for system development and things like that. Which methodology will be required for requirements management, engineering, testing, integration, validation, role analysis of the state of the art, reference to previous projects, possible follow-up activities after the phase A conclusion, and possible partners. This is not mandatory. Somebody have ideas about it, good to share. So the projects are 7 projects. It will depend on how many groups will be formed, if we can develop all of this, or just 5 of them, or okay, it will be upon your choice. Okay, so the first project is a spinning orbital space station. To experiment artificial gravity, relevant parameters could include type of structure, size, rotation speed, Coriolis effect, radiation protection, and others. Orbital workshop for debris and wreckages recovery, processing, and reuse. Moon industrial plants for extraction of helium-3, oxygen, water. Moon industrial plant for production of fuel. Near-Earth objects, mining industrial plant for production of fuel as water materials. Moon energy production plants from solar, nuclear, other sources. And the biggest one, an ONECT.
Hello. Hello. Maybe a provider also the jet has okay. Let's go ahead, however. I think maybe some of you know about Adriano. He was a scientist, an American scientist at Jet Propulsion Laboratory, I think is a branch of NASA. And he wrote the famous book Colonies in Space, where he hypothesized and designed big cylinders, rotating cylinders, or big toruses with a city built inside. So by rotation, they get artificial gravity. And there are several further projects based on that concept. That concept was called Iceland 1. And now, for instance, at British Interplanetary Society, they conceived Jerry Stone considered an Iceland 0 that would be a demonstrator of that, so with a smaller diameter just to demonstrate the concept, and so on. So, building an on-air city would be an interesting exercise to think about how many inhabitants could live there, and how many years could be realized, taking the materials from where, from the moon, from the asteroids, or where. Okay, making a speculative design of what could be done on this thing. So now you will get some paper material by Rashida that will be these cards, where for each project the basic requirements are indicated. Okay. Simplified standard for work package description is also included in the printed material. And okay, this is all. So the first thing now is to understand how many of you are technical matters studied, technical disciplines. Could you raise your hand? Oh, almost all. Oh. Let the hand raise it so you can count on 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? 12. Okay. Down. How many are politics studying or international? 1, 2, 3. Okay. 4. And how many administrative? I mean, managers or so some of you are both technical and administrative. That's very interesting. So my suggestion is to make your groups minimum 3 person, choosing inside each group to have at least 1 technician, 1 politician, and 1 administrator. So, okay, I don't know how could we proceed maybe to stand up and all technicians on one side. All the politicians outside. I don't know. You already know each other, so you can make
I can say. Hello everyone. Hello everyone. We are group 1 and we realized a project about artificial gravity, and the project is called ESS V2, and we now will present.
So we started out with the question of why artificial gravity. There's a lot of space station work that's been done over the years and over the decades, but it's all been in microgravity. I'm standing in the way, sorry. How the human body responds to artificial gravity, how materials form in artificial gravity. There's a bunch of research still that needs to be done. A lot of questions still left unanswered. So having a space station that can produce artificial gravity and harnessing that environment for scientific research was one of the main drivers behind this from the government perspective of looking to fund or open an RFT for a space station that can produce artificial gravity. One of the other things that we looked at was in a more mature environment, as government starts to look to take into the space a bit more, look at other ways to contribute to the ecosystem. In a terrestrial environment, the government does a lot of economic stimulus and boosting within its local community or within its sovereign space or territory. And so what does that look like if we take that same approach of economic stimulus, economic boosting into a zero-G environment? And we try to find ways of exploring that within an artificial gravity space station. We can jump on to the next slide, please.
Yeah, okay. About the user requirements. Yes, about the stakeholders, so who is involved in this project? We think about researchers and we think about researchers and public and private space organization, and also tourists, because we want to exploit these stations also for tourism. And linked to tourists, also new space and new space. We think about companies and industry, because our new space, tourism is developed especially by companies, private companies. and also governments. Next slide. And so about the user requirements, we developed 5 phases. And the first phase is from 0, so from the beginning, and lasts 3 years, and to realize the first part of the station. And this phase will be on exploitation, about the exploitation of the resources, because we want to use the resource from the moon or from other celestial bodies and exploit that resources in the station. The second phase is the phase 2, from the 3rd year to the 7th year. And in this phase, we want to develop scientific research and how you see, for example, on human performance and on biology, on plants, animals, and something like this, and also microgravity and civil engineering. So all the part of research. And in the 3rd phase, we want to use this research to make tourism also for pleasure, so for leisure, but also to try to help or to help people with I don't know, pathologies, and to allow these people to have health care in gravity. And then we have the 4th phase, which is about the manufacturing. So try to solve the problem we found in the 3rd phase and manufacture and try to solve that problem. And at the end, we have phase 5, which is from 15 years, so from the end of the whole construction of the station to the end of the life of the station. And this is for the full exploitation of the station.
In terms of the scientific and technical requirements that we were looking at for the station, we were going to opt for a torus, or rather that classic donut shape, inspired by some of the early sci-fi publications and presence in popular media at the time, and some of the earlier pioneers in the space. We were proposing for a 100-meter radius torus or donut for the shape, and to be rotating to produce at a particular speed to be able to produce 1 G at the ring. Also for the actual tube, we were looking for a 4-meter diameter. So that's, you know, akin to like 2.5-ish meter ceiling. You can take into account, you know, enough around the outside for your walls and outside structure. And of course, enough life support facilities and offerings to house and habitate a crew of, you know, scientists or researchers for the scientific part. And also appropriate power to support and supply all the operations on board as well. And in terms of the where or location, we wanted a balance between not having to constantly keep the station boosted and also close enough to allow readily accessible resupply and transport of crew on and off the station. So we're opting with a MEO orbit.
So basically the main constraints and challenges of doing this kind of station is, of course, how to build it. So where do we get the materials? Are we kind of producing them immediately in space? Are we taking everything there? Are the models produced on Earth and then like the ISS, or each subsystem is built in space? We tend to opt to this approach due to the size of the system, of course. And then there is also a very important challenge that is how to initiate the rotation to achieve the necessary speed to make the gravity happening. So there are these two main constraints. And another constraint that we have discussed is how this will evolve with the time. So, for example, if to do tourism, we use a part of the torus, or we do a second torus just dedicated to the tourism activities, and how this will play a role in the process of building the station. So there are here plenty of constraints to be defined and decided. So, of course, the main issues of a system like this are related to radiation. So we know already from ESS, we need to have this accounted for. Then you have all the resupply issues. So being a much larger station with plenty of people, like 20, 30 people, so you will be depleting much faster all your stocks and all your needs. Of course, you need to produce something inside. This will be something to be further addressed. So then you have all the liability concerns with the responsibility of having the station orbiting the Earth. All the organization structure that will kind of manage the activities between researcher, tourists, operations, maintenance, all of this will need to be set up. Then, of course, a huge main issue is the budget. So this is not a cheap station, of course. Then you have to account for all, let's say, during the many years of the operation, which is 30, we need to account for space debris, not only the ones we can produce, but also how they can affect our operation. And then, of course, all the decommissioning topic after the end of the life. So we have defined a work breakdown structure and work package description. We define it on the optics of a government. So we identified 6 packages, so they are related to management, project management of the activity. We thought that being so, let's say, out of the blue technology, they will need to do our supplier first and in orbit demonstration with a scale model that they prove that this can be produced, assembled, and also it is producing the gravity we are looking to. And this will validate that this is possible to be produced. Then we go to the real deal. So a full scale model will be made and produced and assembled. On a later stage, with package 4, we will do the station acceptance test and evaluation. And then we are ready to receive the first astronauts. And then we have all this period of operation, resupply, routine, and maintenance, etc. And finally, we have this activity of the commissioning. So, basic schedule. So, regarding basic schedule, it was already partially introduced by Claudia, but then we have defined a series of milestones. First, milestone 1, in-orbit demonstration. 2, ESS V2 assembly and ready to start the acceptance test. And then we have 3 milestones that will be being ready to receive the first astronauts, first tourists, some years later, and then finally the commissioning. And then.
So in terms of cost and funding of this massive station, likes of which we've never seen, so the phase A can be financed with a private-public partnership. Thank you. With all the stakeholders that we mentioned earlier being involved, the basic costs of creating the station, we're talking about cutting-edge technology. So we need to make a study. We need to make sure that the TRL levels of the technology are demonstrated to show that this is actually feasible to do, and what technologies are not at the readiness level to make sure that we get them to the readiness level before we can actually make the station happen. So another aspect is to make sure that we manage the cooperation between all the different stakeholders. So of course, this won't just be a US station. We need as many countries involved as possible. We need as many stakeholders involved as possible to make sure that this is not just a project that's put up into space and then abandoned, but actually used and exploited. So just the coordination aspect is going to take some time to get the funding and the budget required to go forwards. Of course, we're still in the early stages of space exploitation, so we need government funding for this. So in terms of the actual economics of this, we project this to be actually a profitable station over the 30-year lifespan. Definitely not in the first 15 years, but after the station has been fully built, there should be some actual profits made to justify the cost of this project. So of course, just for the first phase is where the first 3 years is where the majority of the money is going to be put in to make sure we have all the materials brought to space and actually built, and then going forwards, some other costs related to each costs and revenues related to each of the phases activities. I think.
Okay. Agree to work with. Please, say your name, all name and family name.
Sure. Paul, Mr. Adriano, it's fine.
Okay.
João Pedro Moreira.
Okay.
Leonard de Guzman.
Thank you very much. So now. Please, orbital debris. Come on.
I know my
Hello, everyone, and welcome to our presentation by 4 technical people. So we are talking about space junk and our proposal as to how to clean up the mess. So we are providing, thank you very much. So space junk, as you know, is a problem. As more and more satellites are going into being like our constellations, we're going to have collisions causing more and more debris all over the place, causing loss of satellites and then the loss of the use of those satellites, etc. So we're proposing a space cleanup service. Next slide, please. I was like, okay. Cool, thank you. So we have a very basic model here. And what we're proposing is an in-orbit hub or garbage can that will be in LEO with mini robots that will be going out and collecting our dead satellites and bringing it back to the garbage can. Hub, sorry, not garbage can, that's just what I was calling it. Sorry, can we go to the image? Go back to the, yeah, thank you. So basically, we'll have smaller robots coming, collecting the dead satellite, bring it into the garbage can. Once the garbage can is full, we can then recover the materials from our garbage can. Yes.
So the stakeholders for such a project are coming from a broad spectrum. First of all, since we are touching upon these 6, this is 7, I'm sorry. Next slide, please. Yeah, the first one is the international organizations. So, because they are representing the current and future users of space assets and also the world. So, the long-term sustainability benefits, increased safety and security of space activities for current and future generations connects this project to all these sustainable development goals and also the reuse of material as well. Next slide, please. The current constellation providers, they will definitely benefit from this project because it will decrease their costs, potential costs that will arise from the damage-based liability because of the traffic. Next slide, please. Current space asset owners other than the constellation providers and orbital transportation service operators, this will definitely benefit from the safety and security of their space assets. in case of some emergency situations, the system might be get into the situation, adapt to the situation, and maybe even clear the orbital path of current space assets before the satellite enters the collision course. Next slide, please. Insurance providers, recyclers on Earth for these materials, and space situation awareness companies are also stakeholders because they are connected to the project through the output. And yeah, cleaner recyclers definitely will benefit from the material that's brought to Earth. Space situation awareness companies will be employed through the tracking of the assets that will be brought down, and also insurance providers will benefit a lot because the traffic and the problems in the orbit will be decreased in the end. Next slide, please. So for the user requirements.
So these are the user requirements. We proved the arrival on some more technical requirements that I'm talking about a bit. We're trying to create this orbitals platform to be able to get some of the bigger debris. The reason why we targeted the Leo constellation and we targeted more like small sats. Because there's a lot of different kinds of debris in the world. There's the MMLD, the micrometeorite type of debris that is a little too difficult to track of and to retrieve and to think about long-term recycling. There's also the satellites in GEO and MEO that, although they're very big satellites and might get more congested, we felt like MEO was a little bit more popular, especially constellations coming up, and so that's why we kind of targeted that as like a major goal is to clean up the LEO kind of constellation for the small sats. And we wanted to be able to provide like a service for these satellites because in the future I think there's going to be more regulations, there's going to be more restrictions as far as the orbiting, and unless you're pretty some satellites deorbit naturally over a couple of years, some can take longer, and some may not have the ability to propulsion themselves to the orbit by themselves. So thinking more ahead in the future about like these restrictions and more policy. We saw like a need for more companies to need something like what we're providing. Yeah, that's the idea with that. Yeah, we wanted to be able to also retrieve them without blowing them up. I think that's not a really great way to get rid of older debris. I don't think blowing them up would really solve the issue very much. So we're just thinking of ways we could actually retrieve them and reuse them or recycle some of the materials in a way that we can do that a little bit different than some of the other companies that are doing it right now. Next slide, please. So here are the technical requirements, and separated by the main spacecraft that we're launching, which we're calling the collector hub. That's going to be launched, and from the hub, there's smaller satellites like robots that are being launched out that we call the debris. Wally debris. And so some of the requirements for the hub is that, like we talked about, it has to be in Leo, so obviously that one has to be in Leo as well. We have to be able to have some propulsion on it because we don't want that one to also deorbit. We also have to be able to kind of move around and maneuver a little bit. There's some questions and issues with that, but yeah, we also are planning to. There's 3 kinds of satellites that we're targeting. The main one being the dead satellites. So ideally, we'll be able to retrieve them, bring it back, and then be able to power them on our own in our hub. There's some technology being done with that, so we could steal that. There's also satellites that have no propulsion, so that's also another target. And then finally, there are satellites that are alive and have propulsion. So our idea is also to send out like a signal like, hey, we're here, come over here, and so they can use that signal to maneuver themselves onto the hub. And then the debris, the little guys, they also have to have propulsion to get there. They are going to have a lot of autonomous technology to be able to find it. So we're thinking about ways that they could find our satellite in orbit. There already is a lot of tracking on the ground, so we're hoping to be able to use that from other companies that are doing debris tracking, like that satellite tracking. Use that to locate it
It's not perfect, so we're figuring that we're gonna have to use our own kind of methods to find them. So the debris are also gonna have the little wally ears to be able to look and find and pinpoint and grab the other satellites. So that's one technology. And yeah, and then they'll be able to, it has to be able, this is a big one, you know, docking and resetting itself back to the hub. So that's next slide, please. We talked a little bit about LEO, but why it's in LEO. It's popular. That's my part really. We're also thinking about bringing it to space stations. You know, that's how we recycle it. That's still kind of like a question mark, but there has to be like a third entity besides ours and that one's, and then someone else to be able to kind of retrieve that and recycle it a little bit. So we're hoping to work with that. LEO just makes the most sense as far as being able to have that ability. There's a question about people. It's not going to be crewed, of course, it's a spacecraft, satellite. So, but it does have to have a lot of autonomous technology. So, next slide, please. That's one of the issues. So, autonomous technology is very new. Using computational methods is also very new technology, but it has been done. It is being done right now with some current research. So we still can leverage that, although there's going to be technical issues there. But a big one is that LEO is really big, so we can't really reach everywhere in all the orbits. So we're just kind of focusing on like an area around our hub, and then if you're there, great, we can catch you and recycle you. If you're not, just wait till we orbit around and get to you. Finding the right orbit, you know, and there's several different kinds, different populations. And of course, these are just some of the main things that we're doing, and there's always going to be some technical issues there. There's not much detail there, but, you know, future work. That's about it.
Right, okay, yeah, so the main issues we've got is who on earth is actually going to pay for this? Sorry, I realise it's nearly dinner time, so we'll apply for this. Who on earth is going to pay for this? That's one to probably cross when we get there. One that's kind of a little bit of an inconvenience, less of a bother, is that dead satellites don't really position back to Earth, so we would have to go around the houses to get that one quite figuratively. There's, as we learned from our lecture with Jeffrey Hoffman the other day, there's quite a lot of energy required to change your orbital position information. So if we're going out sending robots to collect things. And then finally, is there actually any profit to be found in the reuse and the salvage of things? Don't actually know, not a clue. But how much effort is required to do that for the money that you get back? Go to the next slide. Lovely, basic WBS. It's a very basic one compared to what we just had before. We'll just skip to the next slide so that everybody had a great deal, if that's okay. Basic time scheduling, I should point out I'm not a space engineer, I'm new to this, so I don't really know time schedules. We've done it as a kind of iterative, repeating process, so I do maybe a 10 to 12 month design stage in engineering, then go back to it again. How long that would take, who knows. Again, we'd be looking at the business viability while we're doing it, and would you launch the probe, you'd have to sterilize things, testing. Could be a case of years to get this all working. Go to the next slide, please. Perfect. Cost and funding. Number one, who on earth is going to fund it? I've already said that, I'm not going to touch that one. Would probably have to get involved with capital, venture funding. Could we, for example, I'm not suggesting it's a Kickstarter, but could we, for example, use something like that where, for example, you give us some money and we will recover a bit of a satellite and send it to you so you can put it in your lake house. I've got a bit of satellite, what rich people like. Could governments or the United Nations require people who actually put the debris up there to actually pay for it to come back? They probably could, whether people would, that's another thing. Could we use insurance to pay for it? Again, who knows? And then the costs originally would be high, but then as this would be or could be transferred to creators, an incentive for them to design in ways for their satellites to deorbit. Could we go to the next slide, please? Business plan, again, we're not business people, so who knows. Originally we'd be making money from the deorbit dead satellites, but as obviously we want to design ourselves out, could we then transition to using a smaller kind of hub or little bin system to go into the reuse and salvage or even the repair? Could we use R&D to implement a kind of automatic satellite deorbiting systems? I don't know whether anyone's heard of deorbit. They kind of do that, so we're kind of stealing off them. And then could we work on creating some policies? We've seen what it's like in lectures, so probably not. I think that's the last slide. Is there another one? Sorry. It's another slide. Perfect, right there. Thank you.
Also, you can say your name, please, quickly. Quickly, very quickly.
Yeah, my name is Matthew Dahl.
Sorry.
My name is Matthew Dahl.
Okay.
Josefina Salva,
Edeni sorsam.
Katie Kane.
Now.
We're two, but we just went through two, so let's not do it one. You did what? We're doing things about you guys, so let's not do it.
Okay, let's go.
Oh, we're at the
Before we go, I just want to tell you that here we have some books. This is my book. This one. It costs only €12. Somebody wanted this here. And this is the Special Lessons Manifesto and all the 9 founding documents of the Special Lessons International. This is €10. So if somebody wants to make it, here they are. Please, go ahead.
Hi, so we called our project Artemis 95 because when you go to fuel up in Europe, it's always 95, right? So Artemis 95, and there's our first customer, I guess. Let's get started. So we started with the abstract, so kind of like a summary of everything else. Last thing we did, first thing I presented. So Artemis 95 is a fueling plant to be set up and operated on the moon. It enables long-term cost reduction of space missions. This is pretty clear. There are already plans to do that. I don't know if you guys heard, probably you have, like Musk said, the first thing that he wants to do on Mars is generate fuel before you do anything else. So that's like the first thing you're going to do, and we're talking about actually setting up a plant. So this benefits, of course, it's kind of a big thing, but you know, it's not like we have an established industry. So yeah, benefits the space industry and humanity. I mean, we're talking about leaving Earth and being able to sustainably exist in other locations. We have to start with fuel. So we do believe in that. And a proof of concept. So we need to see the conversion of moon surface materials to rocket fuel is possible. We know there are already companies that are converting it into oxygen. We have to see if it can be converted into fuel. I personally am not familiar with a company that's already doing that. In terms of the constraints, so of course the fuel production quantity and the cost. So basically financial viability. And of course it needs to survive the trip to the moon. There were other things that we tried to keep brief here. And we'll go to the next slide. In terms of challenges, so constructing on the moon, okay, we're talking about 1/6 the gravity. So of course this is going to be very different, and that's going to mean that we're going to have special training and special facilities. Technological readiness, I touched on this before. Is the technology even there? Is the technology financially viable? Budget, we'll talk about that in a later bullet, but this is going to be obviously very expensive, and it will be a long time before we're going to see a return. And personnel selection and training. When we're talking about setting up an actual fuel station, so you're talking about people that are going to have to stay there. So you have to pick people that are able to go to the moon, willing to go to the moon, stay there. There's a lot of constraints that we need to think about. When we talk about the physiological side later on, in terms of the long-term vision business plan, so we're talking about in 30 years, which kind of seems maybe a little ridiculous, but that's kind of the way we have to think about something like this. Like if you're talking about a natural resource, like I don't know, natural gas or something, you have to think that far ahead because it's not going to pay itself back within a few years. So at that point, when we're talking about this is being set up and it's being used regularly, and it happened for a long time, so there's going to be a reduction of Moon and Mars project costs, obviously, just like Starship is going to lower the cost, so if we're able to refuel on the moon, that's going to lower costs. And because it's going to lower costs, it's going to allow new capabilities, new projects. More people are going to be able to go. It's going to open up not just to government, but to companies and to private individuals. And can you click again? And the nicest benefit, can you click? That and another one. Money, 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 money. We got to be a monopoly. Wait, go back. It's cute. Okay, thank you. So, I mean, it's cute when you're the monopoly. It's not cute when you're on the other side. But this is like a major issue. Why are people trying to mine asteroids? Why are, once you're there, if you set up a fueling station on the moon, very low chance somebody else is going to do it. So, we were talking about this, like, Musk, of course, Falcon 9, oh, it's cheap now. well, when he pushes everybody else out of the market, I'm feeling that launch costs are going to start going up. So when we're the monopoly, that's a bonus, not from some other people. Okay, next one. So work breakdown structure. I kind of feel like going into every single one of these is a bit too much overhead, but yeah, I mean, basically there's an initiation stage, which is covering a lot of what you guys are talking about, like with the stakeholders and defining our project goals. And then we have the planning stage, execution, you want to control it, make sure the quality is right, and closure. We actually touch on this more when we talk about the actual tasks. So we kind of go more into detail. So let's go to the next slide. We understood we have to fill out this whole form. That looks like we're the only ones.
No.
Okay. All right, because this took a long time.
Oh, yeah.
So anyway, okay, so I don't even remember what the abbreviation is.
Yeah.
But anyway, so what's the title? It's so we know the name of the project is Artemis 95. We're talking about a moon fuel plant. So what are the major components? So major components are going to need some type of an extractor, a miner that's going to take out the material. You need a processing unit. You need some type of intermediary storage. We need some type of long-term storage. We need a fueler at the end that actually connects to whatever spaceship or whatever is going to be there. And we of course need a crew habitat because we are going to need quite a few people. I'm sure we're going to need much more, but that's very high level thinking. And in terms of the start event and the end event, so this has to kind of start with R&D because to our understanding technology isn't there yet. So it starts with R&D and there are different stages to talk about, and it'll end with operations that you can actually refuel on the moon. So this is like very optimistic, but in any case, the planned date to begin R&D we said would be in another year, because what we had talked about was, okay, so by the end of 2022, we'll be able to send out the SOW, and then we have to get in the results, and it's going to take us 6 months to pick someone. So within 6 months to pick someone, and they can start, which is very optimistic from experience. But okay, let's say that's how long it takes. And then operations is going to be after 5 years. So R&D starts, and within 5 years, which will probably be late, but it's sort of reasonable. It's not, it's not crazy unreasonable. So the input at this point, because it's a new technology, academic research, I mean, we were thinking maybe there were other companies, maybe, but we kind of just stuck to that for now. In terms of the task description, so there are quite a few tasks. So of course you need to train the personnel. We talked about that. You need to do a proof of concept. We need to, this is in terms of like also a little bit the order. You need to manufacture on Earth the various components. Yeah, train personnel is going to be just here. Sorry. Could you go before? Good. The previous one. Launch materials, personnel, setup, fuel plant, operations. Okay. It's not interesting to go over everything. Next slide. Okay, deliverables. So deliverables, once you guys go through that, it starts from the beginning, it ends after 5 years. So we have requirements review, we have a preliminary design, then a detailed design, then you have a prototype. Once we have the prototype, there's probably going to be a Delta design. I think it's very ambitious to have one Delta design, and satellite that I'm running, we have like 3. But let's say there's one. Set up the lab facility, have a quality review and acceptance review that includes the tests. Then at this point, basically you have everything on Earth ready to be launched, or at least an initial system. When you can start training your facility, you can try training your crew. Then you have the final review and you launch it. Standards, ECSS, it's kind of like it's the European standards as opposed to NASA. All right, next slide. SOW.
Just keep
the last slide. Okay, well, and then the life and health problems. Oh, okay, fine. All right, we talked about that. We talked about the social and psychological isolation. People get depressed. Yeah, people get depressed. They're on the moon. Anyways, yeah, next slide. Rough estimation of costs. So we said 5. What?
5 billion.
5 billion.
That's crazy. I thought it was 58 euros.
5 billion. Some people said 100 billion, and they said 2. Did we settle on 5? It actually is based on some input. Never mind. There was some thinking behind that number. Okay, I guess. We wanted to talk about the sustainability goals, so affordable and clean energy. That's an interesting question, but because the moon isn't really filled with a lot of living creatures, how much are we gonna? So I would call it clean, and there's no atmosphere. Is it going to be affordable? Yeah, in 30 years. And industry innovation and infrastructure for sure. And that is a goal. think it would necessarily reach like the first time you succeed, but that would be the goal when we talk about 30 years. Yeah, I think that was it. Oh, Hana or Hana, whatever's easier for you. Spelled Shana.
It's also.
It's not as hard as the Indian names. The Indian names are hard.
And I would like to, but I think we need question. Sorry.
Yep.
So we have 3 minutes left and 2 groups present and they want to go to salsa.
Sorry.
We have the next activity starting now, we're past time.
Your presentation is still missing on my.
No,
Right? You send it?
Yeah, no, but I sent it like 9 times, to be honest.
Let me see.
Final one.
Only honestly,
It's like, that's final,
Oh, yes, I had it.
But it's so useful about the survey, you know?
You turn the key on. Then look like Tesla.
So, okay, you want to come now?
No worries.
That's my camera. What's
Quickly do it.
Why don't we
No.
think through?
Well, here.
You mean this is.
I'll just stand there. If you have to go to salsa, go to salsa.
I don't have to.
Okay, just really quickly.
Then, let me say one thing, because I don't know if somebody just already stated. I definitely need that all of you send an email to me, because we have to stay in touch, because at Special Lesson we have several committees taking care of these things. And we would like to continue your work with us, if you like, of course. Because I am sure that all of you were stimulated today, and you feel to continue this work to get a better work, because of course 1 hour and a half is not enough to develop anything. So I will leave you my as I have some more of them.
Guys, you're gonna be super quick about it.
Okay, so orbital debris, recovery and reuse.
Yes, so we kind of took a different approach in terms of like we are NASA and we are going to Lockheed to kind of tell us what they're going to develop. So we set like really high level requirements. We didn't actually go into a deep technical design. I think that's kind of a misunderstanding, but we're going to wing it. So we're good. Next slide. Sure. So there's also concern when it comes to debris. Debris is our topic. We have decided to focus on one problem that's really difficult sometimes. Considering the new space economy, considering how easy it is now, space is becoming way more accessible. There's more and more players going in there, getting their satellites in there. On top of it, there's a lot of debris already there. It wasn't really controlled very well in the past traditionally. So there's a high risk. So space safety is an issue. To add on top of that issue, there are many mega constellations which are now being placed there, thousands of new satellites. All of that all together creates a potential risk of damages and collision problems that can lead to outages here on Earth, and all of that can lead to gigantic losses for those companies. So our problem that we would like a company or someone in our statement of work to solve is how to remove debris from that area of LEO lower Earth orbit and design a solution that will take care of this problem in the future. So considering the short lifespan of a lot of those satellites, we have to make sure that there's like after 5 years or after they stop operating, they're not just going around there as a debris. So yeah, so we're solving a solution. The problem is there right now, but we're also taking care of what's coming next.
Okay, so I'll also throw a little bit of the technical side. There's an extractor that takes the debris out of orbit, puts it into an incinerator that can be on the International Space Station. Over there, the debris is heated up, and there's a centrifuge that divides the materials, and you can get raw materials out of it. The stakeholders will be new satellite manufacturers and some companies that want to remove their satellites, as well as ensure.
Should we say these are stakeholders?
Yeah.
Let's go through that more.
Thank you. User requirements. So we need. These are the user requirements.
Next, basically, they need to have a foundation for their company to go forward with this proposal, right? So we're gonna slide you back. So we're gonna judge you next.
Okay.
So our technical requirements, we wanted to keep at a really high level so we don't actually like guide the companies towards a certain design. Like our said, we had kind of gone down a path of designing like an incinerator and all this, and then got confused. So here we are. So just at a high level, we defined, like we need command and controllability, we need to be able to reach LEO, we need a mission lifetime, that kind of thing. Next slide. So where are we going? LEO, and then how are we going to do it? We're going to have an unmanned incinerator operation. There's no reason to have a man powering this vehicle next. Our main constraints are things that you can think of in terms of legal. People aren't necessarily going to want to take their satellites down, but also this is new technology, so issues with that. The debris locations are multiple locations. We're not going to go to the same place over and over. Short timeline, resource constraints, technical issues. It'll need maintenance. It's subject to wear and tear over the lifetime. Next. Our basic schedule, we define, the general timeline. So the RFP is going to drop now, then we'll have our system requirements review, our preliminary design review. Critical design review will start in AIT, and then we'll launch in December of 2026.
Okay, very briefly without details, we divide our work with just our structure into three main parts. This is project office, project management, space segment, ground segment. All of these basically describe the most important subsystems that will need to be developed. Next. So this doesn't push out, but this is our work package description. Basically, we zoom into each of the phases: feasibility study, preliminary design, critical design, and they describe major things that need to happen. Feasibility study, basically we want to come to analysis of environmental requirements policies for companies to understand it, and we want them to develop baseline design. Next. And then deliverables. Preliminary design, user requirements, technical requirements, concept design of both space segment and ground segment. Next. Now in critical design phase, we're going to zoom into the design, finish it with a baseline design of both space and ground subsystems and segments. We're going to do interface definition as well as the test prep for the next phases. Deliverables, critical design review report, and integration readiness review report. Next. MIT, manufacturing assembly integration and testing. We are going to use our input as our deliverables from past phases, and we're going to basically test the subsystems. We're going to manufacture our parts and assembly them together. Then we're going to, as a flight model, we're going to put it all together, and then we're going to do qualification testing to space qualifying, basically. That ends with flight readiness review and final report. Yeah. Next, please.
So we said about 30 million budget. I originally proposed 10 billion, and she told me I was being an American. So we're going with 30 million as our budget. We're expecting, say, like Boeing or et cetera, to pay the 30, or the government to pay the 30 million, and then Blue or whatever company to match or pay the rest. Next. Our business plan, we really were thinking with this incinerator idea, we're going to burn the material that we're collecting and we'll turn it into raw materials that we can reuse again in the space industry. So our idea was to preserve the actual material that we were collecting.
But on top of it, we are hoping to do some of the return from the companies who are going to use this solution as a service in the future. So for them to avoid litigations or legal problems from potential collisions with their old satellites, they're also going to pay to the company delivering the solution. Okay, yeah, that's.
And it's called the Bruise.
Yeah. Oh yeah, y'all missed the name. That was the last.
Okay, who's the last? Sorry, the more is the event, right? Extraction of inventory. Yes.
Yes.
Again, salsa and dinner will be really fast. It's very similar to what the other team does. So next slide. So basically, we want to, with the Artemis program coming to the moon, and want to create an easy access to space and beyond. So we want to actually utilize what's through NASA, what's on the moon, to actually mine for water and oxygen, for fuel for satellites, and then beyond for the asteroids. So next, please. Next, please. Hopefully you did. Okay. So yeah, the key stakeholders are basically, in the summary, it's going to be governments. We want to make sure that we have provided service for the governments, and then obviously the commercial side, because that's how we could actually make profit. And we put general public just because people have a incentive that space is bad. This way, when we take away, we generate our own revenues, they think we're good until the part about polluting those sites. That's a different story. So next, please. Yeah.
Considering the user requirements, we consider proper filtration of moon dust in living and working areas of astronauts, enhanced radiation shielding suitable long-term work, proper thermal insulation and regulation for workers, provide proper and human working conditions. Next, please. As far as the tech requirements concerned, validate mining potential of different regions in the moon, and in order we would like to put a constellation of satellite in the south of the moon in order to track the water presence, and we would like to validate the tools required for extraction moon's condition. In addition, assess the feasibility of using robots in mining. Test the process of splitting water into oxygen and hydrogen molecules on the moon. Next, please. Where in the south pole of the moon, where there is a lot of water, and drones, robots in future mission at the different regions of the moon. But this is how. Next, please. Main constraints and challenges. We are taking into account also the legal challenges of distribution of resources in the moon and asteroids, technical challenge of making an ideal drill for the moon, moreover, creating a self-sustaining ecosystem for moon workers, and these are the principal points. Next, please. The main issue are initial stage requires significant earth resources before the moon plants become self-sustaining. In addition, we took into account also the long-term effects of gravity on the workers are unexplored, and moreover, the lack of study of lunar water could have unforeseen issues. Next, please. This is the UBS for our project. In particular, it's standard, so there is an initiation process, the planning, the execution, the control, and the closeout. It's very standard, and it's detailed on this slide. Next, please. And
yeah, so just to summarize quickly, this one is basically starting with the actual material for the drill itself to mine water. Next, please. Just a simple timeline, basically government and private side was after that. Next, please. So, all right, so No, the next one, please. Yeah. All right. So just in terms of funding, yes, we put approximate numbers, but in the sense it has to be. Yes, good. Yeah. So we okay. So just in summary, funding by the government, opening up the door to the private. So it's going to be private investment coming in, and the business plan right here. It's up to your reading enjoyment. Thank you very much.
Great work. I am really surprised for the quality of your work. I'm not recording. I'm really surprised. Yeah. So I hope you were inspired and you enjoyed this workshop, and I think we can do more of these things. And I would like very much to put in contact each group to some of our experts that are trying to develop activities on these topics. So, okay, let's see us again next time, or even on Zoom if we cannot be present. And I'm sure we can do something excellent. Okay. Thank you.
That's very good.
Wait,